Ladies and gentlemen, welcome to Size Isn't Everything, or BFDLAC, a fast lossless audio compression algorithm for drum sounds. Quick overview of the talk. I wanted to make you familiar with the problem domain, which is the BFD software drum instrument that I've been developing for 13 years. Some quick characteristics of sampled drums, and then we'll look at the actual BFD lossless audio compression format, compare it to some other algorithms that are out there, most notably FLAC, and then see what we can do to make it go faster. And then, of course, the arm-wavy future thing. BFD is big drums. We never say what the F stands for, but you can use your imaginations. If you come from the Christian rock market, it's faithfully recorded, of course. It's a software instrument. It's available in all the plug-in formats, Mac, Windows, and a standalone app. And its main feature is that it's sample-based, full multi-microphone recording studio simulation of a drum session. And these are one of the probably the most complicated parts of recording any band, just because of the sheer number of microphones and instruments involved, because a drum kit isn't just one instrument, it's many, and they all interact, and it's hell. We at F-Expansion would say that BFD has been the industry benchmark since 2003. So we have some awards and lots of third-party support to back that up, and it is quite simply quite large. The user base is also big, so we have tens of thousands of users at all various skill levels. The user base is also varied. We have musicians who don't have a drummer friend. We have musicians who have a drummer friend, but drummer joke. Electronic drummers who want to get a better sound than they're getting out of their TD-10 or 20. And the all-important microphone, the headphone option for parents with drum-enthused children. Producers and educators as well. The educator one is interesting because we fully simulate having a big multi-channel need console-y type thing with all the effects. So if you're an SAE type institution that's trying to get 30 students learning how to do multi-channel drum engineering, then it's a bit hard to have 30 Neve desks for everyone to use. So you can simulate that with us. How big is BFD? Well, BFD 1 in 2003 was 9 gigabytes, an outrageous size. Outrageous because at the time, a lot of people didn't have DVD drives, and we had to make the bold decision that the only way to ship this thing was on 2 DVDs, and there was much moaning on KVR. There's always much moaning on KVR, but that's separate. BFD 2 that came out in 2007, we went up to 50 gigabytes. And this is now 5 gigabytes per kit. We managed to use a customized version of FLAC to compress that down onto 5 DVDs, and then during install, unpack it to waves for efficient streaming. We couldn't use FLAC during the actual streaming because, unfortunately, FLAC is too slow. We also had the customized FLAC because FLAC has a maximum of 8 channels, and BFD has more than that. Often a lot more than that. BFD 3, 2003, we go up to 160 gigabytes. This is now becoming quite large indeed. We're getting up to about 16 gigabytes per kit, and DVD drives are starting to disappear again, thank you, Apple. So we also just noticed that people weren't going into shops to buy physical copies anymore, and it was now becoming feasible thanks to everyone using Steam games and the use of the idea that downloading 40, 50 gigabytes for a game or a music application is quite normal, but you can also buy it as a USB stick. And if you add up all the expansion packs that have been developed over the past 13 years, we have over 1.2 terabytes of sound. So some users out there who obsessively collect BFD stuff have massive hard drives full of drums. So maybe we can help them in so many ways. Why is BFD so big? So you can see from the photos of these recording sessions, there's microphones absolutely everywhere. So every hit in the BFD world may actually have 11, 12, 17 separate audio channels for that one hit. So none of the ambience or microphones are simulated in BFD, they're all absolutely real recordings. They're also very long recordings. So we have a disk streaming engine. When you hit one of our virtual toms, you will often get 10, 20 seconds worth of the sound decaying away naturally. Of course, we have to put a limiter because toms and cymbals will quite happily go for 2 or 3 minutes if you let them. So we also hit the drums in many locations. We will hit each of those locations possibly 100 times and maybe 200 if you're a particularly obsessive BFD expansion pack developer, no names. We will then hit them with all those variations with different types of sticks. So we've now got the articulations times the velocity layers times the articulation types. And then we'll do that for everything else in the kit. And then we'll do all of that for several kits and call it a day and say there's an expansion pack about a year worth of audio editing later. Fun facts. If you play all the BFD data back to back, it would take 115 days to listen to everything. This is also a 2.75 kilometre high stack of 1.44 megabyte floppies. And after talking to a finance friend, it's about 1 day of his trading data. So 13 years of my life is equivalent to 1 day of his life, and I feel great. We have one kit being about 16 gigabytes. We must do disk streaming. Even in days where we have rampant memory all over the place, users will insist on using other software at the same time, which might also have disk streaming and huge RAM requirements, so we have to be nice. A typical drum pattern when you're playing it in BFD will often have several dozen voices. You know, I've quoted 50 here. So you've got 14 microphones, each in 50 voices, so you've 700, 800, 900, maybe 1,000 channels of sound playing. And times that by the sample rate and by 24 bits, and you're getting up close to a full SATA drive, you know, old school rotational ones worth of bandwidth. So we really need to squash the data down to get it up off the disk, up into the chip as fast as possible. So what's great about data compression? It obviously reduces the amount of disk space you need. But of course that then enables all the sound designers to say, great, that's room for me to put even more microphone channels and even more velocity layers and come up with new wacky ways to hit the cymbals. It's just, you know, constant warfare between trying to make things smaller and people just going, great, that's extra space I can use up. And we obviously want to improve the bandwidth, the amount of data we can move from a disk up into the chip where we can then start synthesizing things. So more voices, reduced dropouts from when the disk can't keep up, and ever longer cymbal and tom tails. Problem is that if we're introducing data compression, CPU has to do more work, and we have to do, or I have to do more bookkeeping and accounting as to where the hell we're up to in the disk streaming. So, been looking at this for quite some time. What do we need? We need something that saves lots of disk space. Doesn't have to be the absolute best algorithm in the world to save hundreds and hundreds of gigabytes. Like if we only got a 2-to-1 compression ratio, there are obsessive compulsive BFD collectors out there who would suddenly have 500 gigabytes spare. We'd like it to be very, very low CPU overhead when it's decoding, because we have so many channels to decode at once. And this is one of the reasons why we couldn't use FLAC, because it can't keep up. I wanted the file format to have a very, very simple and predictable data structure for a number of reasons. One, it means the amount of things I had to keep in my head, or that the computer had to keep in its head while tracking all the various disk streams would be reduced. I also wanted to be able to go hard on multi-core optimizations and SIMD instructions. So I wanted something that was simple enough that you could just do bulk parallelism all over the place rather than getting too tricky with the maths. Also, avoiding tricky maths makes for a much nicer day. And one of the things we can also do in BFD is not decode channels if you don't need to. So if somebody mutes some channels on their mixer, and we know about that during the decode process, we don't have to decode them, which is fantastic. So, can we trade some compression ratio for a much higher decode speed? First of all, let us look at a drum sound. The start of the drum sound, you have a large burst of basically noise as the energy is transferred from stick to resonant object, and then as the energy settles down into the membrane and the shell or whatever type of drum physical characteristics it has, the noise reduces and you start getting tones and things appearing, and there's a long exponential decay. In the case of toms, the harmonics may be harmonic, and inharmonic in the case of cymbals. Something to note when you have been doing 24-bit drum sounds for a very, very long time is that about a third of those 24 bits are noise. Users will get very, very excited about all this old gear. Steve Albini, he puts everything through Tape Man, and that pack is one of the noisiest BFD packs we have. So essentially, over the last 13 years of shipping BFD data, 1/3 of it has been junk. I'm sorry, your hard drives are filled with noise. But that adds that special authenticity that the users are absolutely attracted to. And we've tried to do things like doing 20-bit versions of BFD data and just getting caned on KVR again. So we will ship the noise, a vast intellectual and company profit loss effect. So let's have a look at some other lossless audio compression algorithms very, very quickly. So things like FLAC, Monkeys, Audio, Short, and WavePack, they all have very similar schemes where they're using some sort of linear predictive coding with some sort of rice noise residual encoding. And they all tend to focus on taking a short chunk of audio, predicting what the bulk of the samples are going to do, subtracting that, and then just encoding whatever's left over as the noise. So, and they're all designed to deal with full mixed audio. We're not. This is very, very useful. So, heavy-duty predictors are overkill for the non-complex signals that we're dealing with in the world of drums. So, to illustrate this, I've tried to colour in all the bits of a sound that are basically unused bits. So, the sooner we can get down to encoding just the bits that we need for any one particular time chunk, the better we're going to be. So yes, the vast majority of the drum is a tail that gets smaller and smaller. The harmonics are often simple in a drum, or very, very unpredictable or inharmonic if they're a cymbal. So what we're going to do to make us, to allow us to use fairly not smart encoders is we're going to use very, very small blocks. So we're just going for a sort of a very rough idea of which way the sound is going, and then trying to get down to encoding the noise as quickly as possible. We're also going to allow ourselves to exhaustively search our space of encoding algorithms and noise combinations, because we're all about the decode. We don't care how long it takes to encode. All about the decode. As it turns out, because everything's so simple, the actual encoding is faster than FLAC as well, but that's not one of the priorities. And we know that the noise floor is unavoidable, so what we're going to try and do is basically say that local to each one of the audio blocks, there's probably going to be about the same bit depth of noise. So we're just going to make it fixed, which means we get to use SIMD later on. And a quick segue over to interleaving. So most of you will be aware that audio data is often interleaved between left and right channels, and this increases the locality of all the samples you need for any one point in time in your sound. So if we look at non-interleaved data, there's a big data file position difference between the start of the left channel, L1, and the start of the right channel, R1. So you'd pretty much have two separate disk streaming operations in that case. Interleave means that you can be reading both channels at the same time, but as the number of channels increases, you start hitting this annoying thing where, as you get up to about 16 channels, you're now getting to a cache line every time you're jumping from one sample to the next. So what we'd ideally like is a sort of hybrid format down the bottom where in small time chunks, all the samples you need for any one channel are right next to each other, but then the samples for the next channel are still close and nearby, so you can sort of stream them efficiently in one bit, and then when you actually go to do the synthesis, all the samples for any one particular channel are right next to each other in a time-local way. All right, quick look at the BFD structure. It's a riff-like type thing. It's got chunks with chunk lengths and nested. There's a format chunk, a bit like WAV, with enough information that you can work out how long it is and what bit depth it is. There's an index chunk. Let me just get down to that one. Oops, too far. Yep. One more. There we go. There's an index chunk which has fast offset references to 8K sample points in the file, so that if you're trying to rapidly move to a part of your encoded file, then you can do these sort of bulk chapter moves, which is something you can't do with a lot of compressed audio formats. That a lot of them are built for streaming, and they don't have the idea that you might want to suddenly jump to the middle of a compressed file. Often you'd have to decode all the way to try and work out to get to a particular sample. So we're going to use one of up to 16 micro block encoding sub-algorithms. I've only got 10 in use at the moment, so I've got some up my sleeve still for later on. And we're going to encode the remaining noise with the lowest bit rate as possible, but at a fixed bit depth for any one block, so that we can use SIMD. So a frame, we have a single byte as our frame header, and all it does is say there are this many channels in the frame, and that's consistent all the way through the file, and we can just use that as a, am I at a sensible place in the file structure? Yes, the number's what I'm expecting. Fantastic. The block header byte, so all the algorithm smarts are actually encoded only in 8 bits. We have 4 bits for which of the 16 algorithms it is, and another 4 bits for what the error depth is. And because we have a fixed error size, error signal bit depth, that block header byte exactly maps to an exact length. So again, when we're trying to skip through the file very quickly, we can hit this one byte and go, right, I know that there's now 197 or whatever it happens to be bytes in this frame, and move on, which is great if you're trying to get ahead. BFDLAC block encoding sub-algorithms, they're, again, quite simple. There is no compression. We couldn't do anything, sorry. We have zeros and constants, just a median with an error signal, first order, second order linear prediction, linear regression, and that's pretty much it. They're the ones that do 99% of the work. So not very smart at all. So let's look at the no compression available. This is the fail case. But because we've only got 1 byte as our header, it doesn't increase the size of the block too much, but annoying. We couldn't compress, we actually made it bigger. They tend to be the blocks at the start of samples when you've got that initial noise burst of the stick hitting things, which are often the bits that you've got pre-cached in your RAM anyway, so they had to be decoded, so may as well not have them decoded in the first place, so kind of all right. 0, 30% or 35% of BFD channel data is 0. Again, if we're not shipping noise, we're shipping zeros to the users all these years. That's because some microphones just stop capturing a signal well before other ones, but because you've got an interleaved format, you have to have everything going along anyway. So efficiently encoding 0 is one of the most amazing things that BFDLAC can do, and because we're only doing that with 1 byte. Great. FLAC cannot encode 0 as efficiently. So, then we've got a median, which is, again, you calculate a median, you work out the error signal. Gradient, I've got a picture for this one, give you a slightly better idea of what's going on if you're not aware of signal plus noise models, but we're all coders, so that's fine. Differential encoding, first order, second order, that kind of thing. This one really annoys me because lots of the others quite happily SIMD away, but a differential encoding, you've got this dependency of one sample being needed to be calculated before you go on to the next one. But I was thinking as I was writing up my talk that if you started in the middle and then had differential encoding on either side as a sort of middle outwards algorithm, then you could watch Silicon Valley as your small company gets bought by a larger company and you're working on an audio compression algorithm and it all gets a bit meta. Right. Some second order linear prediction type stuff, and a bunch of algorithms that we don't actually use anymore from early days, which was just doing little tiny blocks inside the bigger block and no longer used. Diff has taken over it. So, BFDLAC versus FLAC. So The numbers I'm going to quote are what I generated for the 2015 Australian Computer Music Conference, which was before I started getting heavily into this indie. But let's see what we get. So this is a 2013 Haswell i7, 3.2 gigahertz, lots of SSD, lots of RAM, and we're going to do the entire BFD3 data set. Right, fight. Yes, so FLAC gets down to 21% of the original size, and it decodes at 873 times real time. So that means you can decode 873 seconds worth in 1 second. So it's about 83 cycles per sample. BFDLAC gets to 25%, decodes at 2,000 times real time, so it's 36 cycles per sample. So we're already going about 2.5 times faster than FLAC, which is pretty cool. So 4% larger BFDLAC, 250% faster. This is good. This is nice. This is like, yeah, full point. Take that, FLAC. But as I was optimizing the code ready to present at the ACMC, we got a little bit better. So we're now at 10,000 times. So now 7 cycles per sample, which is pretty damn cool. So yeah. All right. But wait, there's more. Now I've started playing with some AVX2, and there's a particularly good instruction that we're going to have a look at that has enabled me to get down to 4 cycles per sample. So it's like guts everywhere. So when you're getting up to this kind of speed, even a solid state drive can no longer deliver enough data that BFDLAC can decode. So that's good. That's way more than we need for a typical drum pattern in BFD. So I'm sure you're all familiar with these guys. SSE gives us 4-way vector operations, and AVX gives us 8-way and 16-way vector operations. But the one I want to bring your attention to, which is particularly good for BFDLAC, is 4-way variable bit shifting of vector operands. So this is where you've got a different bit shift for each of the 4 32-bit words in your register. So down the bottom here, I've got an example of packed 7-bit ints for a 7-bit error signal. So the capital letters are like the normal bits of the int, and the lowercase version with the little underline is the sign bit. So this is what we've got stored in the BFDLAC format, and we want to unpack it, assuming it's some weird 8-bit only version of BFDLAC, where all the letters that correspond to one of the integers and their sign bit go into this sort of location where the sign bit's aligned at the end, and there's no crossing of the 7-bit ints across byte boundaries. So what we want to do is we want to load up our SIMD register and then shuffle the encapsulating bytes that correspond to any one of the error values into each of the 32-bit words. We want to do a logical left shift to bring the sign bit up to the most significant bit location. This is different because if you start moving your 7 bits through your 8-bit boundaries, then it's going to be different for everyone. We want to get rid of all the bits that don't belong to a particular noise signal integer, and then arithmetically shift them back to the target bit depth, which would then copy the sign bit all the way through, and then stick it back out the door. And here's an example of the 9-bit error signal decoder. And I've tried over here to give a little description of what's going on in the lowest 32-bit word. So up the top, hang on, let me use the highlight, the powers of highlighting. Right, so the first thing we're going to do is shuffle all the bits that shuffle all the bytes that encapsulate any one of the integers into their own word. Using the shuffle, we then left shift to bring the sign bit up to each of the most significant bits for the 32-bit words. And that's my favorite new AVEX instruction ever, because each one of those can have their own separate shift size. And that guy really made a big difference. We then get rid of all the junk bits that actually belong to other integers, and then arithmetically shift everything back to where it should be for the given bit depth. BFDLAC actually gives you the option to have everything encoded at 24-bit accuracy, but then if you're going to say like a demo version or BFD Eco, a smaller version of your application, then you can generate 16-bit resolution stuff or whatever you like. Yeah, so you'll see that the arithmetic right shift has copied the sign bits all the way in, so lots of little A's. Now, it's very marvelous, very fast, very, very nice, but it is extremely specialized. If you try and encode just general song audio, then BFDLAC will probably get you 20% space saved, so 80% of the original size. But it does very, very well in drums. Often we will see cymbals and things coming down below 10% of the original size. So drums, great. General purpose audio, not so great. But there are other monophonic, especially exponentially decaying monophonic sound sources like pianos that also encode quite well, as it turns out. So we're now exploring what else can we deploy BFDLAC on. Yes, so FLAC is still the one for general music, as long as your music doesn't go beyond 8 channels. So BFDLAC is very much a specialized trade-off between speed and size, but an extremely good one that we've traded 4% to get a, hang on, does maths, 2,000% speed up. So this is very, very useful for us. Now, what are we working on at the moment? I've tried to wrap BFDLAC into one of the audio format juice decoders, and got that running on an iPad for the first time, which is exciting, because now I get to play with neon. I haven't played with neon before, and it looks like a very, very good match for what BFDLAC needs. We're now exploring, maybe there's other people out there that would like to license BFDLAC, so sorry, BFDLAC is not going to be an open source thing at the moment. I want to get more SIMD, because SIMD's fun, and get more smarter sub-algorithms in there. And that's pretty much it. So this is BFDLAC. You have survived an audio compression algorithm talk. Thank you very much.